Okay, so apologize in advance. I think my webcam is a bit broken, so I can't really,
Okay,
share
all
my
right.
thing.
It's not an issue.
All right,
It's not an issue.
awesome.
So I welcome everyone to this day 17 of quantum communication. And today we have a speaker who is a PhD research scholar at Nanyang Technological University. So we welcome Mr. Sheikh Mohammed Abdullah bin Hanifa Marikan, and I'm going to read his short biography. So Mr. Sheikh Mohammed Abdullah bin Hanifa Marikan is first year PhD student at the Center for Quantum Technology, Singapore, where he works under the guidance of Professor Alexander Ling. His research is centered on space quantum key distribution with a particular focus on developing instrumentation for upcoming satellite missions. In parallel, he is contributing to space situational awareness projects, studying methods to track space debris and assets to ensure the safety and reliability of space-based quantum systems. His journey in quantum research began in 2017 when, as a junior college student, he participated in QCAM, an experience that proved to be a transformative and set him on the path toward a career in quantum technologies. He later pursued his undergraduate studies at Nanyang Technological University, Singapore, where he broadened his exposure by completing the IBM Qiskit Summer School and engaging in an A-star research internship. Mr. Abdullah has maintained a strong connection with QCAM, returning as a volunteer and shadow lecturer where he assists in quantum key distribution labs and mentors students. His dedication to physics education and outreach extends further. He has served as a tutor for underprivileged students and continues to design initiatives aimed at nurturing curiosity and appreciation for science among young learners. Beyond academics and outreach, he finds balance through board games and weekend walks, appreciating moments of clarity away from technology despite being immersed in cutting edge quantum research. So, we are glad that you accepted our invitation to be a speaker in this FDP, and I hope participants will enjoy your topic, which is satellite based communication. Over to you. You may take the control of the session. Thank you.
Awesome. All right. Thank you very much, Professor. And thank you all for having me today to deliver this talk on satellite quantum communication. So let me just have a moment to share my screen. Microsoft PowerPoint. Awesome. Share. Okay. I think this is visible. Is this okay for everyone?
Yes, it's visible.
Okay. Thank you so much. So thank you, Prof. My name is Sheikh. I am a PhD student at CQT, and I work with Professor Alexander Ling on enabling satellite quantum communication in the Singapore Optical Ground Station, which is a facility that is dedicated to supporting quantum experiments in space and also expanding the space industry within Singapore. So I'll have a chance to talk a bit more on this Singapore Optical Ground Station a bit later in this presentation, but this talk will be focused on developing an intuition and understanding of the challenges associated with performing a quantum experiment in space using satellites. So I hope by the end of this this talk, we can by the end of this talk.
Sorry to interrupt you. I just wanted to tell you that basically we can take 5 minutes break around after you complete 1 hour, maybe 5 to 10 minutes.
Sure, awesome.
So that we can split your sessions into 2 videos because we are live streaming this on YouTube also. So we want to split this into 2 halves. So at after 1 hour, you can take 5 to 10 minutes break. And secondly, the participants are actually muted in this webinar. So they will be posting their questions on the chat window. So you will be able to take them on your own, or we should read it for you.
I can click it on my own. All right.
Okay, so probably you can check the chat windows. They will be sending questions through the chat window. Thank you.
Awesome. Okay, in that note, I think maybe I'll take some time after a few slides down just to do a little check on the chat to see if there's anything that I missed out. Is that okay? All right.
Yes, perfectly fine.
Okay, yes. So as I was saying, I hope that by the end of this, I can first of all illustrate how satellite quantum communications plays in the global scale of a quantum network, how it places within the scheme of building a quantum safe network, both using satellite quantum communication and quantum communication over deployed fiber. And the key parts of the lecture include understanding some concepts and constraints that are relevant in designing a satellite quantum experiment, right? So working in a satellite environment, working in a space-based environment is particularly different from working one in the lab or in the field because of the difficult environments that satellites have to operate in, that is including temperature variations that the satellite will encounter, thermal radiation, and even limitations of how much watts you can draw from your solar panels attached on your satellite. In the next stage, we'll understand the anatomy of a satellite quantum communication experiment. So it goes from source, how you generate the photons, the channel, which is the atmospheric channel that you traverse, and the detector, how you detect and how you process this information. And in the next stage of the lecture, I will talk about some past, current, and future efforts in satellite quantum communication that also talks a bit about the experiments that we are trying to do here at CQT. Okay, so first I'll just give a quick overview, or rather a quick motivation of why we should care about having satellite quantum comms, right? So in this picture over here on the left-hand side, I have a picture of the QT 3.0 processor, which was published in a paper, I think in March 2025, which is a 105 qubit superconducting state quantum circuit that was, I think, published by the folks at USTC. And they showed significant quantum advantage over a regular supercomputer. And this is just a representative of all the progress that has been made in quantum computing, not just in superconducting quantum computing, but also in emerging platforms on which we use quantum computing. So for instance, the February Majorana one chip by the Microsoft Azure team. So there is a huge push for researchers to work on quantum computing due to the advantages that it provides to how we can accelerate certain computations. However, this is not without its threats. So one of the key threats that quantum computing poses for communications, its ability to decrypt, or rather its ability to as a threat towards algorithms such as the RSA algorithm, which we use to encrypt sensitive data and sort of communicate with this level of encryption. And not just this, but the ability of quantum computers to also work, or rather to have this ability to process information, could also potentially be used for emerging crypto systems in the future. So in this report, in the Quantum Threat Timeline report, they surveyed all the researchers working in quantum computing, and they asked them under what time scale will quantum computing pose a threat to us. So in this case, it will be how much further in the future will the quantum computers have the potential to break RSA encryption in under 24 hours. And they polled several of the academics working in this. And over the next 5 to 10 years, not a very large percentage of academics actually, not a very large number of academics actually believe that quantum computing will be mature enough such that it poses a significant threat. But on the time scale of 15, 20 years, there's a growing trend that these researchers believe that it poses a real threat. And why we care about it now is that there is this migration timeline that we have to play with, right? So over the next, let's say, 10 years, where the threats start to materialize, we need to consider the shelf life of the data that we have, meaning to say at which stage does the data stops becoming sensitive, right? So this is data from people who have, let's say, deceased or lapsed financial data or so on. We have to couple that with the migration time. How long does it take for us to build our infrastructure such that it's quantum secure? And the combination of these two timelines must be less than the threat timeline. Otherwise, we put ourselves in significant risk. So that's where we have to understand what are the efforts that allow us to mitigate these quantum threats. So these operate on a couple of fronts. First, we have quantum key distribution and we have post-quantum algorithms. So post-quantum cryptography algorithms are cryptographical systems that are resistant towards quantum computing. So this can be some combination of mathematical difficulty and so on and so forth. So two of which that are sort of highlighted by NIST were AES-128 and AES-256, highlighted in this green box, and they have an effective key strength and security level against quantum computing of about 128 and 64 bits, which is comparable, which is effectively quantum safe. Whereas the existing algorithms like RSA and ECC effectively have zero level of security against quantum computers. However, AES-128 and AES-256 are symmetric, meaning to say that they require some knowledge of pre-shared keys. So in the future, how quantum key distribution places within this context of a quantum network is a post-quantum cryptography algorithm working in tandem with quantum key distribution, working together to provide us a quantum safe network. So essentially, the natural choice for quantum key distribution would be photons, right? Because photons are weakly interacting with the environment. And this is also very convenient because we already have existing infrastructure that support optical communication, and that is optical links, so optical fibers that we have that enables our internet. So that is convenient. However, optical fiber has an attenuation that scales with its distance, right? And that is very difficult when we want to enable a quantum key distribution network, because quantum signals, like photons and so on, cannot be noiselessly amplified. And in order for us to reach intercontinental distances, right, we require some kind of technology based on quantum repeaters, which are extremely, it's really very challenging. It's almost as challenging as building a quantum computer. So we need to rely on a way to scale a QKD network in the absence of quantum repeaters, right? So where we are in CQT, we're in Singapore, we are a very small country, and it's only about 40 kilometers from edge to edge, from coast to coast. So in principle, in a place like Singapore, which is highly metropolitan and very small, satellite to ground QKD may not be necessary. However, to reach the intercontinental distances, to reach other places, we'll definitely need some kind of optical link that scales much better. So one of the proposed methods to scale QKD is by using optical links from satellites, right? And the reason for that is because even though the atmosphere is very lossy, when we establish a link from satellite to ground or ground to satellite, only the top 10 to 20 kilometers of the atmosphere actually causes significant attenuation. So in this graph here, this is actually adapted from the folks who did the MISHIAS satellite, Yin and Pan Jin Wei, in 2017, and they showed that their satellite to ground link only has an attenuation of about 35 decibels, whereas over optical fiber, in the same distance, about 1,200 kilometers, scales intractably like 192 decibels. So in the future, we imagine that a satellite QKD, or rather a quantum safe network that uses satellite quantum key distribution, will play as a node that transfers information or allows us to communicate over intercontinental distance and lodge itself within the wider optical comms that we have, right? And of course, efforts have also been made towards building ultra low loss fibers that are far less than the 0.16 decibels per kilometer, such as hollow core fibers, but that's a conversation for a different talk. So there are generally two flavors for satellite quantum comms and quantum comms to begin with, and that is discrete variable QKD and CV QKD, so continuous variable QKD. Much of the research that has been done focuses more on discrete variable QKD, and in fact, most of the upcoming satellite quantum comm missions will be in discrete variable QKD. So I will limit the conversation to talk more on DVQKD. So, so there are, within the scope of discrete variable QKD, we have two flavors of QKD, and that is protocols that are based in prepare and measure protocols like BB84, and entanglement-based QKD, and such as ECIT91 and DBM92. So in this diagram over here, I just quickly go through is how a BB84 protocol works. So we encode information in the polarization degree of freedom of photons. And the security here actually comes from the complete uncertainty when measuring in ambiguous bases, right? So yeah, in ambiguous bases. But there are side channels for BB84 QKD. One of them would be photon number splitting attacks. So to be insensitive to photon splitting number attacks, it requires true single photons, which is very difficult to implement in a high loss environment. So the countermeasure against that is actually to encode it in two different degrees of freedom. So this is the so-called decoy state BB84, and it improves on BB84 by also sending some decoy states surrounding the signal state, right? So the decoys don't actually contribute towards the key generation, but it allows the Alice and Bob, right? So the two people that are communicating to understand if there is an eavesdropper. So understanding the abnormal statistics that we expect from the signal and the decoys can give us an idea of whether there's an eavesdropper present. And this has been demonstrated on a satellite QKD mission, the earliest satellite QKD mission, and that's MISSIUS, right? So this is one of the methods of or rather the protocols, the BB84 protocols, because they are much more simpler to enable other than entanglement-based QKD. So the other one is BBM92. So this requires the generation of an entangled pair, and either through distributing this entangled pair or just keeping, or if Alice keeps one half of the entangled pair, they can also do a similar measurements to BB84 and perform QKD that way. The important thing about BBM92 is that it potentiates, if you can sort of distribute the entangled photons, we don't have to trust the satellite. So the satellite can act as an untrusted node. And the caveat is that BBM92 is much more difficult to implement because generating an ultra bright source of entangled photons is difficult, much more, even worse if it has to pass through, or it rather has to be done over a satellite. But BBM92 is one of the candidate protocols for entanglement QKD that is currently in the works, and at least at one point in time was demonstrated as far as entanglement distribution in MISSIUS. So having said that, there are a few concepts for satellite quantum communications that we need to sort of hash out first, and that is understanding how satellite orbits across the planet. So there's a very clear classical picture of how satellites orbit, and that's a two-body problem. And this has much research has already been done to this. Satellites have existed in our network for many decades, but there are few. But we have to be sort of very careful when we want to establish a satellite quantum comlink as far as how we choose the orbits go. So typically, we can categorize satellite orbits into three mediums, right? So mediums in this context refers to how far away the altitude of the, or rather what the altitude of the satellite is. So low Earth orbiting satellites are those that orbit in our orbit at about 160 to 2,000 kilometers. So this is where the ISS is, this is where the CSS is, and like space telescopes like Hubble, for example, typically orbit in low Earth orbit. And it's a general orbit, so the inclination can vary. Its period is about 90 to 120 minutes, and it's used primarily in Earth observation, remote sensing, and that's because it has low latency, but smaller coverage, meaning to say that at a particular instance, it takes a very small field of view photo of the Earth. So it never is able to view the whole Earth at the same time. But because of its low orbital period, it has frequent revisits, right? Meaning that it passes over the same spot more frequently than, say, medium Earth orbits or geostationary orbits, and that has its benefits. On the next part is the medium Earth orbit satellite. So this is 2,000 to 35,000 kilometers, and its orbital period is about 2 to 12 hours. And these are used for navigation like your GPS, GLONASS, Baidu, and radio frequency relays. So those amateur ham radio operators typically like to use radio frequency relays so that they can communicate across a satellite constellations. And these provide larger coverage, meaning to say that at any two distinct points in Earth, there's a higher probability that they will have a line of sight with a medium Earth orbit satellite over LEO orbits, but smaller revisits. And then we have geostationary orbits. So these orbits are, these geostationary satellites don't move, they fix over the Earth's surface, but they provide high latency. Now, it is a worthwhile conversation at some point when satellite quantum comms becomes more mature to have orbits outside of low Earth orbits, medium Earth orbits, and geostationary orbits. And in fact, we do have researchers in TNO who are working on developing a satellite QKD mission with a geostationary orbit, and that provides quite a lot of benefits because it's fixed over the Earth's surface and it has a consistent view of one half of the Earth, right? So that means that communicating with a variety of optical ground stations is in principle possible day and night, right? But the orbit that I want to sort of call attention to is this orbit, the so-called the sun synchronous orbits. Now, sun synchronous orbits have a particular inclination, and they must orbit within this tight region of 97 to 98 degrees from the equator, right? And the good thing about sun synchronous orbits, or the thing about sun synchronous orbits that make it very attractive for satellite quantum comms is that because its mean solar angle stays consistent, it passes over a particular ground station at the same time every day, right? Meaning to say that if a SSO satellite passes over Singapore at 10:30 p.m., tomorrow it will also pass by at 10:30 p.m. And that is very good. That has particular advantages because at the moment, satellite quantum comms can only operate in nighttime conditions. So the deeper you are in the night, 12 a.m., so on and so forth, the better your results will be. And that is because at very late in the night, you have very low sky brightness, right? So because the sun is, the Earth is completely within the shadow from the sun, you get very low background noise. So SSO orbits are at this stage probably one of the most advantageous way to perform satellite quantum comms. And beyond just communication and satellite comms, it's also used a lot for Earth observation and environmental monitoring because it provides this consistent lighting conditions. Okay, so right now we are trying to enable satellite quantum comm through what is known as a trusted node, right? And that is if you have two optical ground stations, after each pass of the satellite will communicate with the first optical ground station and perform QKD with it and establish a secret key. So now satellite has a secret key for OGS1, and then when it flies over OGS2, it will perform a similar QKD, and then it announces the parity measurement. And between the two, the OGS, they can actually infer what the other key is. So OGS1 can get the key for OGS2, and OGS2 can get the key for OGS1. And this is presumably secure if the satellite acts like a trusted node. There is ways to circumvent this, and that is by looking at several satellite link configurations. So if we use a downlink to two separate optical ground stations, we can actually potentiate an entrusted satellite node. An entrusted satellite node that distributes each 1/2 of an entangled photon source. And through Bell test measurements, there is no way that these satellites can actually infer any information that way. So at the current stage, there are four sort of satellite link configurations that we can talk about, right? So we have an uplink, meaning that the satellite, or rather, sorry, that the OGS contains the source, right? So it generates the photon and then uplinks up to the satellite. Or there's a downlink, which is where the satellite holds the source and downlinks to the optical ground station. And they might seem the same, but in actuality, uplinks tend to have much more attenuation, about 10 decibels more than a downlink configuration. And that is because as the beam spreads through the atmosphere, when perturbations are much closer to one another, they tend to have worse distorted wavefronts at the free space part, so the part that's essentially space, as compared to downlinks. And it's for this reason that people tend to prefer to perform a downlink experiment over an uplink experiment, right? Furthermore, high quality detectors tend to be not very radiation tolerant. That means that they tend to degrade because especially when the detector is based off of materials such as APDs, silicon, InGaAs, so on and so forth, they tend to degrade over time due to radiation damage. So controlling or having the high quality detectors on the downlink can potentially extend the link time, or rather extend the lifetime of the satellites, right? And then we should also mention that efforts towards inter-satellite quantum communication can also provide interesting sort of network parities, but as of now, still requires quite a lot of technological maturity to perform inter-satellite quantum communication. So, yeah, all right. So with all this in mind, we can start thinking about the anatomy of a satellite quantum communication experiment. What do I mean by anatomy is how, or rather the different parts of a satellite quantum communication experiment. We can parse them into three distinct parts, right? So we have the source that is responsible for photon generation. Sorry. We have the source that is responsible for photon generation, and these sources can either be sources for BBM92 type, so entanglement type QKDs, or they can use prepare and measure protocols like decoy state BB84. And there are basically one constraint, or rather there is a constraint that we have to think about whenever we are designing a source, and that is SWAP, right? And that's short form for size, weight, and power. depending on where your source is, we are limited by the amount of power that we can draw and the size as well as its weight. The heavier something is, the more space it occupies, the more expensive it is to put on a satellite and launch it, right? Furthermore, another consideration that maybe I should have put in the slide is how rugged is it, right? So imagine if you have to put a very delicate photon source onto a rocket and fire it up into orbit, it will experience significant significant thermal variations, yeah, but also a lot of mechanical and vibrations, right? So can these sources be sufficiently ruggedized to survive a launch, right? And then the optical link, where we have to consider the wavelengths, because different wavelengths actually impact the optical link in different ways, specifically how the atmosphere interacts with the wavelengths and how all of this fits into the link budget. And then the optical link requires a line of sight, right? So and the ability for the optical ground station to observe the satellite and vice versa, and establish this line of sight between the OGS and the optical link. And that is non-trivial. And then the last stage is the detection and the processing, right? So this fall into the same swap constraints and things like detector efficiency, duck count rates, and all these other figure of merits actually play into what the link budget will be at the end of the day, and what is the number of secret key rates that we can establish between the OGS and the satellite. So space is a very harsh environment, right? Sorry, I think I got a message. What are the preventative measures planned for all these stages? Good question. If you can just give me some time, the next few slides we will sort of discuss how we design instrumentation to prevent all of this. Okay, so let me carry on. So there are a lot of environmental considerations that we have to take in place because satellites have to exist in very harsh environment, right? Firstly, we get significant material damage due to radiation. So things like our detectors can accrue a high number of duck counts because of radiation damage, right? Secondly, we have to withstand large thermal radiations. So depending on how the satellite is oriented with the sun, one side of it can, be 40 degrees, 50 degrees Celsius, and the other side can be negative, right? So we have this very large thermal differential between different parts of the satellite, and that stresses the photon generation or even the detectors. Because typically detectors need to be cooled down to very low temperatures with thermoelectric coolers, and this needs to be considered when we want to implement a link budget. Secondly, or rather thirdly, satellites typically generate power, or rather, satellites generate power through solar panels. So how many solar panels can you stack on your satellite will determine how much power that's available to you. So this, for a CubeSat, it doesn't exceed 2.5 watts. For a bigger satellite, you can potentially get higher wattage. So this limits the kind of instrumentation that you can put on board a satellite. And lastly is the size and weight constraints. So as I mentioned, putting stuff on a satellite increases its weight substantially, and that increases the launch cost, right? So ideally, you would have the most compact photon sources and detectors, and with all the relevant avionics, and then piggyback off of another launch, right? We'll talk a bit more about that later, but let's start with the photon sources, right? So the picture here is the photon source for a BB84 protocol. So the difficulty of BB84 is that it requires single photons, and that's not always very practical. So how we can achieve this is by using weak coherent. Go back. We can use weak coherent pulses for BB84 protocols. One of the limitations with a design such as this, where you have 4 diodes, right? Because you wouldn't want to just generate from one single diode, because that requires active polarization. So a way for you to manipulate the polarization so that you can get a high enough repetition rate. You can generate more keys for a specific time. And it's very power intensive and very slow. So what the initial design was to use 4 distinct laser diodes, all of which with some degree of polarization, right? The only problem is that this introduces a side channel in that not all laser diodes actually have identical spectra. So the fact that there's some differences between each laser diode and how they are manufactured, right? Even just very small manufacturing condition differences can result in a spectra that is slightly different. So this actually provides a potential side channel for eavesdropping attempts. So on the lower right-hand side is another design of a weak coherent pulse for BB84 protocols. And that uses a single V-cell array that couples onto 4 fibers, each of which are phase modulated so that they provide a certain amount of polarization rotation. And so this was the one that was used as part of the Michias experiment, who performed decoy state BB84 protocols. And they found that doing this is probably the best way that we can get fast and high repetition rate, weak coherent pulses that allows us to use BB84 protocols, right? So the other flavor of QKD is entangled photon sources. And as far as entangled photon sources, we typically use BBO, PPKTP crystals, and SPDC, in SPDC. So on the right-hand side, we have the photon sources that are used for the Michias satellite mission, the PPKTP crystal, in a Sanya interferometer configuration, right? So it uses a pump laser and 2 dichroic mirrors, and then you have 2 output channels at the end. One either feeds into a satellite, or rather one either feeds into a quantum information processing unit, or just downlinks to another optical ground station, and the other one just downlinks to an optical ground station. However, this can be very power intensive and can also be very large. So to the question of how we can bring an object like this to outer space without that is sufficiently rugged such that it is able to maintain its alignment, is that typically the mirrors are also attached on piezoelectric mirrors and a reference laser, so that in situ realignment can occur. So on the right hand side, we have another entangled photon source, and this one was used on the Glacia and Spooky-1 satellites, which we worked on, and that is based off of a BBO entangled photon pair source, right? BBO entangled photon, BBO as a crystal has smaller non-linearity than PPKTP, but is more temperature insensitive, right? And all of these sources can be mounted on invar mounts so that it can so it has good thermal and mechanical stability. And all of these mirrors, all of these alignment mirrors, can be adjustable piezo mirrors. Piezo mirrors tend to also be very low power, so that we can perform on satellite and in orbit realignment, right? So for these 2 entangled photon sources, they have actually already been demonstrated, been sufficiently demonstrated in orbit. So like I say, the BBO was used in the Glacia 1 way back in 2015, and in Spooky-1 with slight differences in 2019. And the PPKTP one was used in 2016, 2017 on board the Michias satellite. Okay, so now we can talk about the optical link, right? And the big thing is atmospheric transmission. The annoying thing about the atmosphere is that it's not equally transmissive to all wavelengths of light. And we can guess that pretty much. So if we use a transmittance model, like the one used in ModTran, which is moderate transmission through the atmosphere, I believe is a paid commercial software, but they also have a web version. And we can use it to sort of identify the peak transmission zones for our atmosphere. And these couple of lines over here are just the wavelengths that are commonly used in commercial off-the-shelf products, right? So 405, 532, 670, so on and so forth. And generally speaking, we see a clear trend of transmittance with higher wavelengths, right? So this intuitively makes quite a bit of sense because typically we use in the past for communications we use radio frequency, which is very long wavelengths, and intuitively we also know that shorter wavelengths like UV rays tend to have lower transmittance because of, let's say, the ozone layer and so on and so forth. So we need to choose a wavelength, right? It's not as simple as saying let's just choose the highest wavelengths because there are other considerations to take place, such as what detectors that you have that fit your link budgets, and other losses that can occur due to a larger wavelengths. So in the MISHIAS missions and in the Spooky missions, we use typically 780 and 800 nanometers, right? Wavelengths. That allows us to use detectors that are that are lower dark count and much more have higher detection efficiency. So, okay. One more thing about the atmosphere is that it introduces quite a bit of turbulence, right? So the atmospheric distortion is a non-trivial matter, especially for astronomical observations, and we can model it with a value called the Fried parameter, or the coherence length of light, or the Fried coherent length, and this value represents the column that, so you can imagine this as a cone that from the optical ground station through the sky, it has clear turbulence, right? So we don't see a lot of atmospheric distortions at a Fried parameter or at a value lower than this value. So a few centimeters, for example, right? And why this matters is that the turbulence profile really depends on your location. So an urban environment, let's say in Singapore, is highly metropolitan. We also are very near the coast, so we see a lot of thermal differentials, and that causes typically worse atmospheric distortion. And we can model it with a value similar to this, with a particular CN2 profile, which is atmospheric turbulence profile. So I give sort of a very hand-wavy explanation of this, but what this essentially means is that when we plug all these values and plug all these models into our satellite link mission, we can see that on a nominal day, we have an 11.1 centimeter Fried parameter, and on a bad day, we have a 5.7 Fried parameter. What this means is that we can resolve things up to about 2.8 arc seconds. An arc second would be 1/36,000th of a degree. That means that any smaller than this, we cannot resolve. We cannot resolve it. And this also gives us the pointing accuracy that we are targeting for towards the seeing limit. If we had telescopes that were smaller than the seeing limit, now the telescope would be diffraction limited, and that would really depend on the wavelength. Okay. These atmospheric turbulence also introduces beam wonder beyond the seeing limit. So we can actually simulate the beam wonder, and this arises from the larger scale eddies that happen on the lower atmosphere. And this really depends on the specific atmospheric model used, but more importantly, when we plot out these models, we need to identify the frequency of this beam wonder, right? So in our case, it was about 87 hertz, which is the knee frequency, meaning to say that if we have a fine steering system or a mirror that corrects for this beam wander, that is about 90 hertz, we can correct for 95% of the errors introduced by beam wander. And all of this really depends on the size of the aperture and the size of the quantum receiver that you're using. And all of this should be within the order of the atmospheric seeing and beam wander. So the long and short of it is that when we are designing an experiment like this, we need to model the atmosphere in as complete as possible in order for us to understand what the size of our aperture should be, because there are diminishing returns, and the size of our quantum receiver. Okay, so now we talk about the biggest losses that we encounter when it comes to optical link, and that is diffraction losses. So we can approximate as a far-field divergence because the satellite is many hundreds of kilometers away. And the long and short of it is that it scales with the inverse square of the wavelength that we use, right? That means that is to say that a 1550 nanometer wavelength would fare much worse because of its wider beam spreading. So we can estimate the loss due to diffraction with this model over here, and it relates to several things. First are the receiver and transmitter aperture. So the smaller the receiver, the more tightly collimated, or rather the larger the receiver. Yes, sorry. Yeah, the larger the receiver, right? The larger your telescope aperture is, the more light you can collect. So you are less susceptible to diffraction because the overlap integral between your Gaussian beam and your receiver is much higher, and is inversely proportionate to your transmitter aperture, right? So the smaller, the more tightly collimated you want your beam to be, the wider it will diverge, right? And R is the slant length. So the distance between the optical ground station and the satellite is not always constant, right? As it approaches you, it will be as close as possible when it's 90 degrees just above overhead, and it gets further and further away from you. Your beam size will actually increase and decrease with the slant range as the satellite. Okay, so I think we have a quick question. Not understanding. Okay, let me repeat what I have to say and try to be a bit more concrete. Okay, so diffraction losses arise as a result of how far your satellite is from the optical ground station, right? So the diffraction losses inform us as to what wavelengths fit within our link budget, fit within our satellite quantum communication link budget. So with all of this in mind, we can actually determine the optimal size of the quantum receiver, of our receiving optics, like our telescope, and our transmitter on the satellite. Crucially, the diffraction losses remain the dominant losses when you want to establish your link budget, right? So having a higher wavelength having a larger wavelength may increase or rather may decrease the attenuation that you get from the atmosphere, but will increase your diffraction losses. Okay, one thing that remains as a challenge for satellite quantum comm is how can you maintain that line of sight, right? Pointing losses, or rather how misaligned your optical ground station is from your satellite link affects your link budget to a significant degree. So maintaining that line of sight between the optical ground station and the satellite is a key part in satellite quantum communication, because small deviations up to microradians can incur quite a distinct pointing loss. So typically the benchmark that we aim for for satellite quantum comm would be somewhere smaller than 5 microradians, and that is limited by the atmosphere, and also provides you with acceptable pointing losses. The question of how we track satellites, how we are able to faithfully maintain that line of sight, we will talk about it. We will talk about it in the later part. Okay, one thing about optical links as well is that because the range of the satellite, the range rate of the satellite changes as it passes through zenith, will yield a Doppler shift. And I don't really want to talk too much about this because it does not really affect very much the satellite quantum comms experiment. But as a consideration for quantum storage based on optical memories that permit a quantum network, this is a consideration. Further, time bin entanglements will also require Doppler shift corrections. But this is a very minor point. Typically, the effect is only several picometers and will usually fall within the line width of your photon source. Further, when a satellite passes over the optical ground station, it incurs a relative polarization shift. So as the satellite traverses through its orbit, it will also slightly rotate, right? And if you are using, if you are performing QKD with encoding information in polarization, you will need to model how that rotation actually occurs, right? And that can be done through understanding the satellite ephemery. So ephemery refers to the orbit of the satellite, the model of the orbit of the satellite, to pre-compensate on our receiving optics, right? So this was done successfully in the Messias mission, and this was also done done successfully in several terrestrial QKD missions. But we can see that when we compensate for this in the basis rotation, we get a much lower quantum bit error rate. And this also plays into how we design the quantum information processing unit. So yeah. Okay, so we have about 10 minutes before the end of this hour. I still have quite a few things, so let me carry on. Okay. So this introducing the TLE in the satellite family gives me a chance to talk a bit about how we track satellites. So we have this format called the two-line element, which is a repository of satellite orbits, right? And these are provided by NORAD and allows us to track with some level of accuracy where the satellite is. So on your right, we have this image that's taken from our optical ground station of a satellite pass, and typically for a two-line element or a two-line element satellite ephemery. Okay, sorry, I thought I saw something. Satellite ephemery, we have typically within 2 milliradians of your field of view. And this is very readily available. But importantly about the satellite, about the two-line element is that we can create this on our own because the last few elements of the TLE is just the mean anomaly, the mean elements, the mean classical elements of a satellite. So we can, if you imagine, we can get a GPS on board of a satellite, and we can use that to generate our own two-line elements so that we don't have to rely on the ephemery maintained by NORAD. But the point is that this provides us sufficient cost tracking, sufficient field of view, so that we can actually maintain that line of sight, but only within 2 milliradians, which is far more than the pointing that we will need, which as previously was 5 microradians. So that's why we need systems that allow us to perform fine tracking systems. And these fine tracking systems must exist on both the optical ground station as well as on the satellite. So this is the environmental considerations that we have to start thinking of, right? So fine steering systems tend to be very power intensive, right? And because of that, we need to, and furthermore, because we are performing experiments in a polarization, encoded in polarization, we will need to ensure that the fast steering systems are also polarization preserving. So as an example, on the right-hand side, I've given an image of the MEMS, so micro electromechanical fast stirring mirror by Miracle, which is space qualified. However, because they actually deform the mirrors using piezo, they are not polarization preserving. And fine tracking systems have huge size, weight, and power budgets. So as an instance, we have this Newport voice port actuated MEMS mirror that we use in our laboratory setup, and it weighs in excess of a few kilograms. So having fine tracking systems on board a satellite can be very difficult. So instead, what is typically done is that the satellite will body point itself as a way for fine tracking system, as a way to sort of track mutually the Earth observer, while the optical ground station will have the fine tracking system, right? Okay, so that's why we've talked about the source and the optical link. Now it's time for us to talk a bit more on the receiving optics. Okay, so on the ground stations, similar to the one that we have on our left and our right, we have a telescope. A telescope will act as the receiving optics for this photon that there's photon that's downlinked to us, right? So the point is that with a larger diameter on your aperture, you can get better a better secret key rate. However, this increases the cost and tracking accuracy because a larger telescope requires a larger mount, and a larger mount, is more massive, so you need a higher reinforced pedestal. And because when things are more heavy, when things are heavier, they are much more complicated to track, or rather they are much more mechanically complicated, and therefore the tracking accuracy will decrease. So we need to consider these four factors: size, cost, and tracking accuracy when we want to scale the receiving optics up, right? And one more thing is that when we scale the receiving optics up, we also incur much more background noise. So all these things need to be optimized for when designing a satellite quantum distribution experiment. Okay, I think we are almost on the hour. I have a few things left to say. Would it be okay if we start taking a break now? And I see if there's any questions that I can address.
So there are, you have already answered one of the questions which a participant has asked. So probably we can take 5 to 10 minutes break, 5 minutes break maybe.
Okay, yeah, there'll be 5 to 10 minutes would be good.
Okay.
Yeah, and
all
then,
right, thank you.
If you have any questions, or if I'm missing something out, or if there's something that I'm not explaining well, please put in the chat. I will try to address them as best as I can. Thank you.
Yes, so the participants, specifically who has posted the comment about not understanding. So if you can specifically say what kind of topic where you were lacking the understanding, it would be much more helpful.
Yeah, okay. I should mention that this research is very interdisciplinary. So maybe I don't give due focus on certain things that you want me to talk about. I'll try my best to explain them in as concretely as possible. Yeah.
Right.
Right.
Thank you.
Very much.
Yeah.